Hello students, welcome to the video lecture 3 of this week, and we continue with our review. The next thing we're gonna review is how to take sets and plot them and make a picture out of it. And in order to do that, we have to define intervals. So intervals, and if we talk about intervals geometrically, that is a line segment. So let's look at this. For example, if A is strictly less than B, then the closed interval from A to B is the set. Since we define set, it would be the easiest way to describe it. All x such that x is greater or equal than A and less or equal than B, and this is for closed interval. And an open interval would be from A to B is a set where x, we take x if x is strictly greater than A and strictly less than B. So now we need the visual representation. So visually we get for the closed interval we have a real line, and it goes from A to B, and filled in circles mean we include the endpoints, but some people use, instead of filled in circles, use brackets. So some people would do it like this: bracket A, bracket B, and they make this line thicker over here. So we fill in the line between A and B. Now we have described closed intervals. Again, either filled in circles at the end, that means we include A and B, or the brackets would work. So this is the closed interval. And for the open interval, you have a real line, and for A you use a empty circle. So this is A, an empty circle for B, and you filled in the line in between. That means you exclude the endpoints. And for the second version, you use parentheses to exclude A, parentheses to exclude B, and you filled in the line in between. So this means exclude, and this means include. So we describe the visual representation for the open interval and for the closed interval. What else could happen? There could be that you want to include the left endpoint and exclude the right one, or vice versa. So basically, an interval can include one endpoint and exclude one endpoint. And such intervals are called half open. Such intervals are called half open. But again, if one half is open, the other one is closed, so some people call it half closed. All right, so let's look at few situations that are possible. So you can have interval AB like this, which would be X such that X is greater or equal than A, but strictly less than B. Or you might have A, B like this, which means you take all x's such that X is strictly bigger than A and less or equal than B. So we use set notation to describe it. In other situations, that is possible that the intervals can extend forever to the right or forever to the left. So intervals can extend indefinitely For example, we can have something like a to positive infinity. That would mean all x such that x is strictly greater than a. And visually you would get for a, you have to exclude it, and it has to go all the way to the right. And also you might have something like this, from minus infinity to b, and suppose we want to use b, so we put a bracket on it, and in the set builder notation we would say from x is less or equal than b. So visually you get b, which is filled in circle, and everything on the left side of b would work. So these are the situations, but we continue discussing sets. So another definition that we're going to need is two sets A and B are said to be equal if they have the same elements. The same elements. And we write in this situation that set A is equal to the set B. So let's look at a few examples for this situation. For example, if we take a set of all x such that x squared is equal to 1, and on the other side we take the set which is -1 and 1, so we list elements on the right and we use set builder notation on the left, but no matter what, the solution of the equation x squared equals to 1 would be -1 and 1, which is exactly the set on the right. So we put an equality sign. In another example, we might have 0, pi, and 3. But on the right side, we might have 3, pi, and 0. Since they have the same elements, we have an equality sign to say that sets are equal. All right, so this is a situation when sets are equal. Another situation is the following. So let's try to define the situation. In this situation, we have this. If every element of a set A is also an element of a set B, then we say that A is a subset of B. And we write A and special symbol, this symbol that means A is a subset. Didn't write it correctly, subset symbol. So one addition to this definition is that we have to know that the empty set, which has no elements, is always a subset of any set. Is always a subset of any set. All right, and let's do an example. First example is relatively simple one. If we take two elements of 2 and 4, it's definitely going to be a subset of -4, -2, 0, 2, 4, 6, and 8. How do we check? We take 2 and we see, is it on the right side? Yes, check mark for 2. We take 4, we see if it's on the right side, check mark for 4. So we can clearly see that both 2 and 4 are on the right side. So 2, 4 as a set is a subset of the right side. And example number 2, if we take all x such that x is a rational number, it's going to be a subset of the set which is x such that x is a real number. Because that's how we build real numbers. We took rationals and irrationals together. So the set Q is always a subset of R in a simple. All right. Another idea that we can discuss in this lecture is this theorem. We're not going to prove it, but again, it's a really interesting one. It says that if A and B are sets, assets, then if A is a subset of B and B is a subset of A, then maybe I should remove this word and say put dot. So let's go back. If A is a subset of B and B is a subset of A, then A is the same as B. I don't think we're going to use this that often, but it's an important result, but worth stating it here. All right. Since we're reviewing, we're moving kind of fast. If we're moving fast, let me know, then I'll try to explain things in a bit more details when we meet in office hours. So next thing to discuss is this definition. It says the following: if A and B are sets, then the set of all members belonging to both A and B at the same time is called the intersection of A and B, denoted by special symbol A, then upside down cup B. And this is a symbol for intersection. Visually, it's really easy to understand. If we have a set A represented by a circle, and we have a set B represented by a circle, these elements that belong to both sets at the same time would be the intersection of A and B. So this set over here is A intersected B. All right. Since we're talking about intersection, probably it's worth to define also a similar idea, which would be called union. So, and then do examples. So if A and B are sets, then the set of all members belonging to A or to B or both is called the union of two sets. Denoted by A cup B. And this symbol is for the union. Now the visual representation would be if we have a set A and we have a set B, then A union B would be all items that are in A and all items that are in B, and including items that are in both A and B at the same time here in the middle. All right, so everything here would be the set A union B. So basically, we take one color and we color it with the same color. So all of this is A union B. All right, so as promised, we'll do some examples. So first one is sketch the set -4, 3, excluding 4, including 3, intersected with the set 2, 6. All right, so let's create our real line to show what the sets are. So let's use the blue color for this set. So we start at -4, so we have to exclude -4, and we go all the way to +3, and we include +3. So this is our set from -4, 3. Then we need to show the set from 2 to 6, so I'll use the red color for this set from 2 to 6, where we exclude both points. So 2 is on the left side of 3, so it's going to be over here. It's going to be over here. And so this is going to be 2. And over here we will have 6. And we take everything from 2 to 6. So since we're taking an intersection, that means what? That means that we look at this interval over here where both blue curve and red curve intersect. All right, so maybe we make a bigger picture. So the picture goes up to 2, then including 3. So from 2 to 3 and the line in between. All right, so what would be our answer? Our answer is 2, 3. Then we have to choose brackets or parentheses. For 2 we use parentheses. For 3 we use bracket. And this is called interval notation. All right, so we have a visual representation, interval notation, and it's also set builder notation. So if you write it in a set builder notation, we're going to take all x such that x is strictly bigger than 2 and less or equal than 3. And this would be the answer for this problem given in many different ways. Set builder notation, also interval notation. All right, we can also just say x bigger than 2 and less or equal than 3, right, as an inequality. All right, so let's move to the next example, example number 2, in which we have to sketch the set from -4 to 2, union from 1 through 5. So let's try to start thinking about it. So we're going to start at -4, which is a filled-in circle. We're going to go up to +2. Then for 1, we're going to put circle over here. And 5 is a filled-in circle over here. So let's choose some colors. Blue for the -4 to 2. So -4 to 2 goes in blue, and 1 to 5 goes in red. All right. So in here, we have to take everything. Since we're talking about union, that means we have to take everything possible. So let's try to see. We're going to start at -4. We go all the way to 5. The only thing we have to worry about, do we include this empty circle or not? Empty circle doesn't work for this set, but it's perfectly fine for this set. And since we take in one set elements from one set or the other set or both, since it works for one of them, it works for the union. Conclusion: our answer will start at -4 and will go all the way to +5. We include -4 because it works for the first one. We include +5 because it works for the second one. And we take everything in between. It works for one or the other set. So that means our solution is in interval notation from -4 to 5, bracket, interval notation. And if I want set builder notation, for set builder notation, we get all values x such that x is greater or equal than -4 and less or equal than +5. And I think that's probably a good place to stop, because in the next lecture we're going to use these ideas to solve inequalities. And I'll see you in the next lecture.